Buenos días, tardes a todos, bienvenidos. Entonces, hoy el ciclo de seminarios del Centro de Geosciences del jueves, retomamos después de las vacaciones. Tenemos el gusto de tener con nosotros el doctor Joshua Garber de la Universidad de Penn State en Pennsylvania, en Estados Unidos. Él es geólogo, es investigador asociado en la universidad, trabaja desde hace varios años en cuestiones de basamento cristalino, de geocronología, isotopía de rocas, petrogénesis. Lo invitamos porque pensamos que puede estar interesado en colaboraciones, ampliar también el escenario, digamos así, de propuestas, tanto analíticas como propuestas, digamos, de estudio que tenemos activas en el Centro de Geosciences. Y bueno, nos va a dar una plática relacionada con una zona de solución, si no me acuerdo mal, en las Islas Cícladas.
No, en Arabia.
En Arabia, ok, en Arabia. Sí. Entonces, como siempre, bueno, pues, bienvenido. Luego paso por la introducción y luego todas las preguntas que tengan. Sí. Muchas gracias. Josh, todo tuyo.
Muchas gracias, Luigi, muchas gracias a ustedes. Para comenzar, muchas gracias para la invitación para hablar hoy con ustedes. Un poquito sobre mí, soy un profesor y gerente del laboratorio LACPMS en Penn State, en Estados Unidos. Pero yo también tengo un programa de investigación del que voy a hablar. Esta no es mi primera vez en el área de Querétaro, as you can see. Así que es muy bueno estar de vuelta. Y ahora pueden escuchar que mi español está muy feo. So for the rest of the talk, I'm going to switch to English, which I hope is okay. So thank you for suffering my English. So I'll jump right into the science and start that part of the talk today. I have a lot of interests, as Luigi mentioned, in crystalline rocks, in geochronology and petrogenesis of Earth's crust, but most have to do with the role of plate tectonics in terrestrial geochemistry. And one of my main topics of study is subduction zones. I'm interested in how they start, the thermal and chemical structure of subduction zones, and then how and why they end, usually in collisional origins. So Mexico is an excellent place to study these, and I do have some interest in Mexican geology, but unfortunately none of them were developed enough for me to talk about them today. But on Earth, the reason that we care about our subduction zones is myriad, right? Hazards are definitely an important part of that and part of my research interests. But one reason that I think about subduction a lot has to do with geochemical cycling of carbon and phosphorus and nutrients that have to do with life on Earth. And for example, if we think about an Earth without subduction zones, all the carbon on Earth's surface would be used up in tens of thousands of years and would basically starve life from developing on Earth. And then this figure is a relatively complicated figure from Horton in 2015, but the argument is that modern subduction zones release CO2, and that's responsible for liberating phosphorus from the mantle that ends up at Earth's surface in various volcanic products. So I'm not going to talk too much about this deep Earth geochemical cycling, but one of the reasons that we should care about subduction zones is because of these deep Earth processes, particularly with respect to carbon and phosphorus during subduction. Okay, so I'm going to ask, and this is going to guide the rest of my talk, a relatively, what seems like a simple question. How does new subduction initiate? How do new subduction zones start? And for the early Earth, this is really an open question. And I wanted to start with sort of a cockamamie theory that's been presented in the literature that maybe it has to do with the role of impacts, that there were meteorites that were slamming into Earth during the early part of Earth's evolution. They would land in these sort of yellow zones here, which would create loading, unequal loading on Earth's surface, and potentially drive the development of new subduction zones. And this is driven by our observations of places like Mars, where we see, for example, Olympus Mons, the largest volcano in the solar system, may actually have been related to a small subduction zone on Mars. So what's really fun about doing this in the early Earth is you can wave your arms and say pretty much whatever you want to. But I'm going to switch to modern subduction initiation. We do care about how subduction starts in the early Earth and develops into a global subduction network that we have today. But one important observation is that new subduction zones have started repeatedly throughout Earth's history. So this is an image from Mike Gurnis and others in 2004, of the Pacific Rim and of the subduction zones on the Pacific Rim. And what you'll notice is that about 50% of these were started in the Cenozoic in the last 65 million years. So even though we care about how subduction zones started on the early Earth, the observation is that they're actually starting now. And it must be a relatively continuous and ongoing process. And we want to understand why that is on the modern Earth. So at its most fundamental, starting a new subduction zone is a force balance problem. This is from a paper that just came out this year. So we can think about the forces that might drive a new subduction zone. For example, far field compression, basically horizontal plate tectonic velocities on Earth's surface of plates. And then the negative buoyancy of a slab as a slab converts to dense eclogite and sinks into the mantle. But then these forces are actually balanced by several other forces that we have to think about. So there's isostasy that we have to consider. There's frictional resistance along the plate interface. There's resistance between the plate and the mantle beneath it. And then there's also the energy released from slab bending. So any subduction initiation problem that we're thinking about in 2 dimensions has to deal with all these balancing forces. And we would like to try to quantify them in different systems and understand which one of these are the most important. And then we could potentially rewind back through geologic time as well. Now that's the 2D case. I also wanted to mention we have to think about this in 3 dimensions, right? So one observation that's been made is it's easier to start a new subduction zone where there is already a subduction zone. And this is the case for Iberia. So this is the Miocene and then the Tortonian to the present. And the argument has been made that that subduction zone is sort of poking through and it's going to wrap around Iberia at some point and start a new subduction zone. So even though I'm mostly going to think about this in 2 dimensions, we also need to think about the 3D geodynamic effects in driving the formation of a new subduction zone. Okay, so lots of other intelligent people have thought about this problem before. And forgive me for flashing up this very complicated slide of how to start a new subduction zone. But at its simplest, these fall into 2 different categories. So remember on that force balance slide, I talked about there's the effect of the horizontal push versus the sinking of the denser slab into the mantle. So on the left are 2 tectonic setting examples where the argument has been made that in those cases, it's the push that's the driving force, that they're initially dominated by convergence, and then they transition to self-sustaining subduction. And then on the right are examples of subduction initiation that authors have argued are dominated by sinking. There may be some sort of horizontal push, but it's basically some sort of loading on the crust that drives sinking of a new slab and then eventually converting into a self-sustaining subduction zone. Okay, so there are lots of different places on Earth's surface where we could try to figure this out. The problem is that developing a new subduction zone erases its own evidence, that when a subduction zone starts and actually becomes self-sustaining, all that evidence of subduction initiation is lost. One place where that's not necessarily true is in ophiolites. And these are pieces of oceanic crust and mantle that are now placed on a continental margin and may preserve evidence of subduction initiation. And in fact, several people have argued that this is definitely true. So this is a cross-section, a really schematic cross-section from the Samail Ophiolite of Oman, where I'm going to be talking about most of my work today, where they looked at the magmas on top of the ophiolite evolving from mostly morgue-like to ones that have a subduction zone influence on them. And the way that we can see that is if in the green unit here is the black line on the right, and note that these are trace elements normalized to normal oceanic crust. It's very morgue-like. It's what we would expect at a normal mid-ocean ridge. But then the later units, the ones on top here, are ones that are depleted in several elements, but they're also enriched in large ion lithophiles. And the argument is that that's a transition from a normal mid-ocean ridge spreading to the influence of subduction fluids as a slab sort of penetrates beneath the mantle, beneath that ophiolite. So this is something that can be seen in many different ophiolites and has been taken as evidence for a new slab sort of rolling back and driving the formation of a new subduction zone. There are also rocks called metamorphic soles that are at the base of these particular ophiolites. And on the right is the modern expression of these things. So we see the ophiolite that's tilted. We see this aureole of metamorphic rocks beneath the ophiolite, and then a series of thrusts going back onto the continent. And the argument is that this is the first increment of subducted material beneath any given ophiolite. And we'll discuss these for the rest of the talk, but the idea is that if these ophiolites themselves look like they have magmas that are evolving as a new subduction zone breaks, the argument is that these metamorphic soles have something to do with that process as well. Now, what do these look like in the field? These are both from Oman. So this is on top on both of these images is the Harzbergitic mantle, and then grading down to the sole beneath them. And I'll show you a picture, a close-up of what the sole looks like in just a moment, but note that this is on the scale of meters. There's a tree for scale right there. So again, in both photos, the top is the ophiolite, the bottom is the metamorphic sole. And what's cool is you can put your hand on what was initially a plate interface at some point. It's an extremely sharp contact now in most of these ophiolites, but you should keep in mind that this structure has been overprinted several times. So it is now a sharp contact. It is a good guess that when it was a subduction zone to begin with, it was not as sharp a contact. And we should be cautious about referring to this as the plate interface. It's also worth noting that there's a really big pressure difference between the ophiolite on top and the garnet amphibolite, or the soles beneath. So the ophiolites themselves are on the order of 10 to 15 kilometers thick, but the pressures associated with these metamorphic rocks suggest on the order of 30 to 40 kilometers depth. So again, even though it's a sharp contact, we might be missing 15 to 20 kilometers of section between those two different rock types. Okay, so what does this look like? These rocks are beautiful. If you pick up these hand samples in the field, the topmost rocks are dominated by garnet and clinopyroxene, so you can see the red and the green associated with those, and then the rest of the rocks are hornblende and plagioclase. And we tend to call this the chickenpox rock, the Rocca vericena, when we go out in the field, and this is what we're looking for. This high-grade rock, which saw temperatures of about 800 to 900 degrees centigrade, it only occurs in the top few meters. So if we go back to that previous slide, that's basically the rocks right here, and then they get lower grade beneath that. Yeah, we'll move on from there. So these metamorphic soles, they're not just cool because they're pretty rocks, even though that is one of the reasons we're attracted to them. They have some anomalous and unique features. So first of all, I think many of you are probably familiar with blue schists and eclogites. I know several of those are exposed on the west coast of Mexico. And those tend to be relatively cool temperatures. So things like 300 to 500 degrees centigrade from going down in a subduction zone and coming back up. As I mentioned, the rocks that I showed you on the previous slide are 800 to 900 degrees centigrade. So even though these are coming from a subduction zone, it looks like they represent the first initial hot stage of that subduction zone before it cools off. Second, there is global consistency in the pressures and temperatures that these metamorphic soils experience. So even though I'm going to be focusing on the Oman ophiolite, there are several cases of metamorphic soils globally in which the temperature conditions are almost identical. So it's clear that it's not just something happening beneath one ophiolite, it's something that happens in every ophiolite, or at least many ophiolites. And then finally, this thermal structure, this really hot metamorphic soil, decays to a normal subduction zone temperature pretty quickly. So in Oman, we have good evidence that over about 10 to 15 million years, this metamorphic soil started really hot, but then that thermal structure dissipated really quickly and it became what we expect for a normal subduction zone. Okay, so I've talked a lot about metamorphic soils. The reason that we care about them, or the reason that they're useful, is we can go back to that force balance problem and we can potentially use metamorphic soils and their ophiolites to understand what sequence of events happened and which geodynamic forces were most important. So, for example, using this figure from Zoe and Wada in 2021, if we think that the sinking of the slab is the most important feature, the negative buoyancy of that slab, we should expect that mantle upwelling will drive metamorphism of the metamorphic soil at the same time that we're getting the formation of the ophiolite in the upper crust. So we can go date the soil, we can go date the ophiolite. If we get relatively the same age, we expect some sort of vertical forcing to be driving subduction in that system. However, if we think that it's that horizontal push that's driving the formation of the new subduction zone, we should expect the formation of a metamorphic soil as that shear zone to be before the ophiolite, which would then form from the eventual negative buoyancy of the slab and spreading in the upper plate. So in that case, the soil would be older than the ophiolite, and that would tell us that horizontal forces are the ones that dominate. Okay, so that sounds really easy, right? You just go date two different rocks, and you can figure out which force is the most important in the system. However, of course, like any geologic system, there's significant disagreement among different authors and different methods, even when we're dating the exact same rocks. So for the rest of the talk, I am going to focus on the Samail Ophiolite in Oman and the UAE, but there's plenty of other ophiolites that you could do this on globally. What's nice about Samail is, this is a Google Earth image, you can see the ophiolite from space. There's no question that it's there. It's extremely well studied because it's very well exposed, and it has really excellent context for this problem that I want to keep talking about. For scale, the ophiolite is about 600 kilometers along strike. So there's plenty of ophiolite and metamorphic soil to go put your hand on in the field. And it generally developed from the northeastward drift of the Arabian Plate into Eurasia, and the Zagros Mountains in Iran are to the north there, and they're part of that collisional system as well. It's also worth noting that these mountains defined by the ophiolite have traditionally been a cultural barrier too, separating the peoples of the coast from the peoples of the interior. And so when you go hang out in the ophiolite, there are lots of castles and forts that have traditionally been used to leverage attacks on either side, depending on which side you were on. Okay, so a couple of things about that ophiolite. It's really not that controversial that there is some sort of horizontal forcing. So this is a schematic diagram of the system at about 120 million years ago, going to about 100 million years ago. And if you do modeling of the plate tectonic evolution of the system, you use G plates, for example, if any of y'all have used that before. It started at about 3 centimeters per year of convergence across the system, but at about 120 to 110 MA, it's debated, the system doubled in its velocity, from about 3 centimeters a year to about 6 centimeters per year. There was another subduction zone that was active at that time, but it was unable to accommodate the entirety of that doubling of the plate tectonic rate. So even if we think that spontaneous subduction initiation or that vertical sinking of the slab is important in the Oman system, it is important to keep in mind that there was an extra push from the convergence of Arabia into Eurasia at that time. It's also not controversial that the ophiolite itself formed very quickly. So in these diagrams are a schematic evolution of the system, and then these different magmatic phases in red are shown up here, in yellow shown up here, and in green shown over here. And these are basically different portions of the oceanic crust of the ophiolite that we've dated by uranium lead zircon. And what you can see is that the ophiolite itself seems to have crystallized basically about 96 Ma, and it was totally over by about 95 Ma. And what's cool is we can use the chemistry of those different zircons and those different rocks to tell us which parts of the system they were in. So evolving from the normal oceanic crust forming at a regular mid-ocean ridge, to the influence of subduction-related fluids, to the influence of subduction-related melts. So as the slab is basically starting to penetrate into the mantle, in the ophiolite crust, it only takes about 1 million years to do that. Now, I should point out, these are zircon TIMS data. These are not zircon laser ablation data. We could never get the uncertainties we needed on the laser ablation system, unfortunately. Okay, so then we also went to the metamorphic sol and we did the same thing. And remember, we're looking for that test. Are the sol and the ophiolite different from each other? And what we see is, so in blue are zircons that formed on the prograde metamorphic path. In red are zircons that formed at the peak portion of metamorphism, so at the hottest conditions. And then yellow and green are late metamorphic products that are as the system is cooling off. In background is that gray bar that represents the timing of ophiolite crystallization. And so if we just date zircons in that metamorphic sol, in that roca varicella, what we see is that it's pretty consistent with the timing of ophiolite formation. There are some zircons that crystallize before the ophiolite, but for the most part, most of them seem to be coincident with the ophiolite. Okay, so we could sort of walk away and say, that's it. It's synchronous with the ophiolite. It represents the sinking of a slab rather than being dominated by that horizontal pushing. However, there was a paper 5 years ago now that dated garnets from the same rocks, and they obtained ages of about 104 Ma, which you'll remember is about 8 to 10 million years prior to the zircons in the same rocks. So they interpreted this as evidence of forced subduction initiation, that it was entirely that horizontal push that was driving things. The development of the sol shear zone, eventually that slab rolled back and generated self-sustaining subduction, which is when the ophiolite would have formed. So they basically came up with the opposite interpretation by dating different minerals in exactly the same rocks. So where this leaves us is we have an order of magnitude difference in understanding how these rocks were metamorphosed and what their metamorphic histories were. So what we want to do for this talk, or where I started approaching the problem, is we're all looking at the same rocks and we're getting different answers, and we want to try to reconcile those to understand how subduction started. We want to understand the tectonic setting of the system, we want to understand the timescales, and we want to understand the heat source for sol metamorphism, so we can go back and quantify the geodynamics. So there are a couple other ways that we can test this. First of all, I want to show you some of the rock textures so we can better understand the metamorphic path that was experienced by these particular rocas varicellas. I also want to use non-isotopic means. So we've been dating things by the uranium lead system, by the lutetium hafnium system, but we want to try to use other methods that don't have to do with isotopes in order to quantify the metamorphic timescales. And I'll talk about this a little bit later when I show the data, but I'll use diffusion chronometry and basically the relaxation of really sharp elemental boundaries in metamorphic minerals. And then finally, something we want to do is check the internal consistency of the isotopic age data. And I'm not going to spend a lot of time on that today because it's tedious and boring, let's be honest, but it is useful, right? We want to make sure that our zircons and our garnets actually plot in the same place in different systems. And that's what I'm going to try to do towards the end of the talk today. Okay, so to do this, my colleagues and I have done about 4 field seasons in Oman, and it's a really excellent place to take students as well, not just for the ophiolite, to basically wallow in oceanic crust and mantle all day, which is really fun. But there's also several structural exposures, for example, of deformed cherts that are great for mapping exercises. So I hope that you all can go there someday. We have sampled the metamorphic soil all along that 600-kilometer ophiolite. And the reason we've done it all along the ophiolite is we want to try to understand these temperature histories and these age differences in different places along the ophiolite and see if they vary. I'm just going to talk to you today about two samples that I've done the most work on from the southern portion of the ophiolite. And it's worth noting that these look like the other metamorphic soils elsewhere in the ophiolite. However, they're the thinnest ones and they're the youngest ones. They give us the youngest radiometric ages. This is one of those outcrops with a stratigraphic column to the left here. So again, going from the mantle of the ophiolite across that shear zone you can put your hand on, down into high-grade rocks, and then into lower-grade rocks beneath that. And those chickenpox rocks only occur in about the top 2 to 3 meters of any given outcrop. So we're dealing with temperatures that we think are coming from this hot ophiolite as it was being thrust over the adjacent rocks, but the length scale over which those form is incredibly short. It's only on the scale of meters. Now, in thin section, what these particular rocks look like, you can see there are clots of garnet and CPX. There's ilmenite in these things as well. So phases that we expect to be forming at granulite phases at 800 to 900 degrees centigrade or so. And then the rest of the rock is all retrograde. So as water was being added to the system, as these rocks were shearing, all of this stuff would have been the phases that were present at peak conditions, and then all of this is later. So I will zoom in on some of these. We focused on the largest garnets in each of the thin sections. And what's cool is it's kind of hard to see, but there's actually a color change between the core and rim of some of these garnets. And then there's a change in the inclusion assemblage between the core and rim of these things. So for example, on the left, there are inclusions of plagioclase, hornblende, and titanite that we think formed at about 600 degrees centigrade. And then the rims of these things have mineral phases in them that we think formed at those peak 800 to 900 degrees centigrade temperatures. So we have pretty consistent evidence that there was a smooth, consistent increase in temperature as this slab was buried beneath the overlying ophiolite. Forgive me, I've turned the garnet on the last slide on its side, but it's the same garnet that we were looking at. So again, core at lower temperatures and then rim at higher temperatures. We performed electron probe mapping of these for major elements, and then we went back and did laser ablation mapping, similar to what y'all can do on your system here, after we did the EPMA mapping. So starting with the major elements, this is a really simple case. In this garnet, we have a core transitioning to a higher temperature rim, and there's a big change in chemistry between those two. In the trace elements, so for example, lutetium here, one of the rare earths, and then in chromium, we see a compositional shift from concentric zoning to oscillatory zoning at the rim. And what we think that is these rocks or these portions of the garnets were below their melting temperature. And then as they melted, they developed these oscillatory zones at the rims. Now, chromium is kind of a nightmare, so I'm not really going to talk about it, but we think that there's some role of overprint zoning in these, that there were other phases in the matrix that the garnet was just overgrowing and sort of adopted their chromium systematics. Now, that other garnet I showed you on the previous page is a little bit more complicated. Again, in the rare earths, we see core to rim zoning that's defined by sort of concentric zoning, and then we see oscillatory zones at the rim of these as well. We see similar features in chromium, again, extremely complicated and just pretty pictures, and so I'll ignore it for any scientific meeting right now. And then in the major elements in this particular garnet, we see really sharp zones between the hotter rims and the lower grade cores. And what's cool about that is these look like dissolution reprecipitation rims. So there was basically an episode at super high temperature where the garnet was being resorbed and regrowing. And we've frozen in evidence in the major elements for those timescales. So what I want to do is use some of these really sharp boundaries, model the temperatures that these things sat at, and think about how long they could have sat at those temperatures. And that will help us discriminate between those 1 million year timescales and those 10 million year timescales. So just a super schematic diagram, we are taking what we think is an initial step function profile, and then we're modeling using experimental data what we think that decay should look like in terms of the elemental profiles that we get out of these things. And then there's some minimum misfit that we expect, which will give us the time that these rocks experienced at their hottest temperatures. And that should allow us to discriminate between the two different geochronologic end members. Okay, so first we have to know the temperatures that these things sat at. So because all diffusion parameters are temperature sensitive. So on the left, I'm showing you a diagram. The lines in red are from our particular rocks, iron magnesium thermometry between garnet and clinopyroxene, and then data from the literature in the background. And then we also did rare earth element thermobarometry as shown in green. So the exchange between garnet and clinopyroxene for the rare earths. And then just because we like to beat this problem to death, we also did some titanium and zircon temperature data from the same rocks, and that's shown in the upper right here. And basically what I want you to take away from this slide is that there are several different lines of evidence that suggest that these particular rocks experience somewhere between 750 to 800 degrees centigrade peak temperatures, and that's what we're going to use for the diffusion modeling. However, there are subsets of the data that suggest a little bit hotter temperatures. And so the timescales that I'm going to give you could be even shorter if we assumed those higher temperatures. Okay, so to start with the major elements, we modeled this particular major element profile just because it was particularly sharp, but you can see there are plenty of other profiles that we could model that would give us the same results. The length scales over which those profiles decay is on the order of about 200 microns or so. And these are numerical models, so we didn't do analytical solutions for these. But on the right, I'm showing you one of the numerical solutions where you can see a solution for 1,000 years, 10,000 years, or 100,000 years. And the point that I want to make from this slide is in order to preserve these super sharp boundaries between different zones in garnet, it's hard for these rocks to have sat at more than about 500,000 years or so. And we tested lots of different diffusion parameters. This is just one of them. But all of them sort of agree that it has to be super short. These rocks basically got metamorphosed and then they got cooled off right away. We did the same thing for trace elements. So in blue are the lutetium profiles. So I have one from the core and one from the rim, the core here and then the rim here. The data and the starting condition in black, and then the model in red. And again, you can see there are many different diffusion parameters that people have published in the literature, but the idea is that these rocks could not have sat at those high temperatures for more than 100,000 years to about 1 million years or so. Okay, that's great. What's nice about these is that these are consistent with the zircon data from the exact same rocks, which we've actually published last year in the Journal of Metamorphic Geology. We see from the zircon data, so just looking at the scales on the left, in this particular rock, it's about 400,000 years. In this other rock, it's about 300,000 years. We get the exact same answers when we date zircon in those same rocks. So we think our diffusion data are pretty reasonable in giving us super short timescales for metamorphism. However, these are inconsistent with the lutetium hafnium data that other people have measured on the garnets. So, of course, because we're suckers for pain, we went back and dated the garnet. And I don't know if any of y'all have done this before, I think several of y'all have. It's several months of picking garnet from your rocks and then sending it off and waiting 6 weeks to get an age and hoping you get everything right all along those stages. I've shown the previously published data in gray, and then our new data are in color. And what I want to point out is, first of all, we get a much younger age. Sorry, my slides went away. We get a much younger age. We get on the order of 98 MA, whereas you'll remember from the beginning of the talk that the other folks got about 104 MA. So we're getting about a 5 to 10% difference in age from the same rocks that they did. The other thing is we went back and did hafnium isotopes on our zircon to see if they plotted in the same place, and it turns out that they do. So our zircon data, even though we get a slightly different age, are at least consistent with the garnet, lutetium, hafnium isotope data in the same rocks. And again, it's consistent with these really short timescales that we get in uranium lead, although we have a slight offset between the absolute time in the uranium lead system and the absolute time in the lutetium hafnium system, which we think is a systematic offset. So I promised not to bore you too much with these kind of data. All I want you to take out of these is that the previous isotopic data have problems, that they don't all play well with each other. And we've tried to go back and actually do internally consistent measurements between the different systems, measuring as many isotopic systems as we can. And now everything plots on the same lines and is actually all consistent with those short timescales that we get from the garnet. So I've thrown a lot of data at you, but I'm gonna quickly summarize that data and then take it further. So we looked at those chickenpox rocks in the highest grade portions of the metamorphic soil from the Samail Ophiolite. We see that there's evidence for prograde burial and heating of those lower plate rocks as they initially subducted beneath the ophiolite. We see from the zoning profiles, from the diffusion measurements, that we get metamorphic timescales on the order of 100,000 to 1 million years or so. We also get the same answers from our zircon uranium lead data, although we're a little bit limited by the precision that we can get on those. And our new garnet data also agree with those zircon data and also the garnet elemental diffusion profiles. And in our new data, we have internal consistency in the isotopes between the garnet and zircon, and that was not true in the previous data that have been published. So what we can take away from this is that that metamorphic soul was sheared out and metamorphosed beneath the ophiolite over extremely short timescales that was coincident with the crystallization of the overlying ophiolite. Okay, and coming back to our force balance problem, these are both images from 2 different modeling papers. On the left in this one is a model of a spontaneous subduction zone initiating, basically vertical forces dominating. And then on the right is the horizontal case where there's some sort of horizontal pushing. And our data are consistent with the influence of spontaneous subduction initiation. It looks like in the Oman system, that lower plate was dense and sank beneath the upper plate, driving extension in the upper plate and the formation of the ophiolite at the same time we have the metamorphic soul. I don't necessarily want to exclude the role of forced subduction initiation, because as I mentioned, we know that the plate tectonic rates sped up right before this ophiolite formed. So it has to play some role in the process. It just has to be a lot shorter than what people were thinking was reasonable for this system. It turns out, though, that that can't be all of the story. When we integrate our diffusion data and our geochronology data, the temperature time histories are just too fast for conductive heating. When you look at this metamorphic soul in the field, all the photos that I've shown you, and especially the fact that you have these high-grade rocks right beneath the overlying ophiolite, it would make sense that there's heat coming from above and metamorphosing those rocks from below. But if we do some simple calculations of the time scales and the length scales for those, we would expect that to be a much longer process, and we would expect it to be something forming over kilometers, not over individual meters. And so our argument from the diffusion data is if you integrate that all together, we have pretty good evidence for thermal pulses right along that initial shear zone. That it's not sort of long-term heating and cooling, it's just one rapid thermal pulse, or at least a couple rapid thermal pulses that are forming those chickenpox rocks in the lower plate. And again, we can come back and see that in the topmost part of the metamorphic soul that's shown up here, and then up here, where we have those garnet and clinopyroxene rocks, these are forming over the scale of meters. It seems that it's much more consistent with the influence of shear heating along that protoplate interface as the source of heat for the metamorphic soul than heating from above, than conductive heating from above in these particular things. Okay, so because I want to show you a couple more pretty pictures, I just showed you data from the 2 samples that are the southernmost samples that I have from Oman, but I have a ton of other samples and I have some preliminary data from those. And the question is, do the other samples that I have from the remaining portions of Oman support that same case? And it turns out that they do. If we look at the major elements, so calcium and magnesium shown in the upper left here, you can see that same transition from core to rim that we saw in those garnets that I showed you before. And then in chromium, yttrium, zirconium, and lutetium, we see similar trace element patterns where we have some sort of subsolidus zoning grading to supersolidus zoning in the cores and rims of these things. So I've now made garnet maps of about 8 different garnets from the metamorphic soul. It takes about 24 hours to do each of these, so it takes a lot of time, and 8 is actually quite a bit, but we see the same patterns over and over again in these rocks, and it suggests to us that we have the same timescales in those. I'm going to skip this slide, but I just want to end by thinking about why we see the same patterns over and over again, not just in metamorphic souls in Oman, but we see them globally. Potentially part of the reason we see these similar temperature conditions in these rocks beneath all ophiolites, not just in Oman, is that it's that role of transient shear heating along the interface. So when the plate interface is developing, it's locked for a while, and then it sort of breaks and shear heats that metamorphic soul right beneath the plate interface. So maybe that's what we're seeing in metamorphic souls, and maybe that's why this is a global pattern, not just something we see in Oman. So to come back to our force balance problem, in Oman, we know that there's some sort of far field compression, but it really looks like the system is guided by negative buoyancy of the slab. And then we also have evidence in the metamorphic soul for overcoming that frictional resistance that's resisting new subduction zones developing. Okay, so where am I going with this? We need to quantify this more. We now have sort of empirical evidence that these rocks were shear heated along that initial plate interface, but we need to calculate the stresses and see if it's actually reasonable for that to happen. I also work with some geodynamic modelers in Europe, and the plan is for us to do some geodynamic modeling in 2 dimensions and 3 dimensions to try to understand why there might be changes within the Oman system and then between Oman and different ophiolites. I also have several iterations of fieldwork planned. So I'm in September, I'll be going to the Bay of Islands in Newfoundland, and then I'll be going to the Philippines early next year. And these are other examples of ophiolites globally that we think formed in the modern, and we want to try to see if we see the same patterns that we see in Oman. Because although I really enjoy working in Oman, I can't just work there. And then we want to test these relationships in other ancient ophiolites as well. So if the problem is how does subduction initiate, we don't just want to understand that in the modern, we want to understand that in the ancient as well. And it turns out in easternmost Egypt and western Saudi Arabia, there's a cluster of Neoproterozoic ophiolites that are about 800 to 900 million years old. And they all have metamorphic souls. So this is the place to go to try to understand ancient subduction initiation. So I'll just leave up my conclusions, and thank you for your attention today.
Muchas gracias, Josh. ¿Preguntas?
No.
Josh, I'm not an apologist, far from it. So this question might be very dumb and straightforward. How can you manage to have, in such a short space, rocks that have been subjected to 1 gigapascal pressure next to another one which have been subjected to half gigapascal?
I'll give you the answer that my co-authors don't like, and then I'll give you the answer that my co-authors do like. But that's a great question. Recently, there have been several modeling papers that suggest the influence of tectonic overpressure. We have to remember when we back out a pressure from a metamorphic rock, we make the assumption that it's purely lithostatic, that it's related to the column of rock above it. However, there is a role for differential stresses. And if we think that these rocks are able to sustain pretty extreme differential stresses on the order of hundreds of megapascals, then it's possible that the metamorphic pressure we're getting out of it is not lithostatic. It doesn't represent the overlying column. It represents the overlying column plus the shear stresses that are being imposed on that particular rock. So one potential solution for that is that the shear heating we see is also driving overpressure, where the shear stresses that we see in the temperature profile are also driving increases in pressure. Maybe those rocks were not at 30 or 40 kilometers. Maybe they were only at 10 or 15 kilometers, but they were sheared so strongly that they ended up with those high pressures. The alternative hypothesis that I don't like is that those rocks actually went to 30 or 40 kilometers in the subduction zone and then got yanked right back out. And there's just no field evidence for that. I mean, when you look at these things, you know, let's see if I can go back further. Oh boy, sorry, I'll get there eventually. Yeah, it is a real puzzle to me that there would be these rocks that are right beneath the ophiolite above them, that the garnet is always in the top couple meters, right adjacent to the ophiolite, right where we expect the shear zone. For these rocks to have gone down, you know, 30 to 40 kilometers, or let's say an extra 20 kilometers or so, and then come back up and been emplaced right next to the ophiolite, that's the traditional interpretation. And I struggle with that a lot.
Yeah, it sounds complex.
It sounds complex, and there's just, you know, the problem is there's no shear indicators in these anymore. They've been totally erased. These rocks have been pretty heavily retrogressed, so we're missing parts of the metamorphic history. But I would say, to answer your question, it's an open question, but the two end member hypotheses are the role of tectonic overpressure, and then potentially those rocks going down and sort of squirting back up the same subduction zones. Yeah. Yeah, thank you.
Más preguntas? Vamos.
Yeah, it seems counterintuitive that the principal force or driving force behind actually having the incipient subduction zone being created is this downdraft rather than the compressional force from given the tectonic stresses on a global scale. I assume that the compressional force does eventually take over once the subduction zone is actually created. And then ultimately, would there be evidence then of that particular imprint following the creation of the subduction zone?
I agree with you that it's really counterintuitive, and yeah, thanks for that point. I think one point that gets made over and over in the modeling papers is if it's a horizontal compression, that is actually the pushing force, there has to be some, you know, uplift at some point. And the problem is for us in Oman, this is happening in an intra-oceanic subduction zone. So there's not much evidence that there was ever any uplift before sort of relaxation and sinking. And then the other point, but others have made this observation. For example, there are some recent papers from New Zealand where there's a new subduction zone that's breaking, and they have evidence, it's close enough to shore that they can look at changing sea level records and they can actually see the evidence of uplift before sort of relaxation. And then, you know, once self-sustaining subduction takes over, the argument is actually that you don't need that horizontal force anymore because you get the transitioning of that slab to eclogite, which ends up being dense enough to basically pull it down exactly. So in Oman, you know, I don't want to 100% say it's totally driven by vertical sinking or it's totally driven by horizontal forcing, because we know we have evidence of both in that case. And maybe the problem is we're asking the wrong questions. Maybe we shouldn't be trying to get these age differences and say like, oh, it's one or it's the other. Maybe we're just looking at different parts of the system. Maybe it was horizontal forcing to begin with, and then the soul just forms as that system becomes self-sustaining and as it sort of locally becomes driven by vertical sinking of the slab as it becomes dense enough to do that. So I'll remain agnostic about it, but I think you make a good point. There's different predictions that we get from different forcings in different timings in different parts of the system. But, you know, we're also looking locally And it's hard to think about the big picture tectonic forces that are driving this in the system. And then one final point that I'll make, just because I just remembered, is after that plate tectonic speed up in Oman, actually right after this forms, everything slows down again. And so even though there was a little bit of horizontal forcing, either the formation of this new subduction zone or maybe something bigger actually started to slow everything down again. So that horizontal forcing goes away. But I think we need to model these things, and we really need to work with people who can model this in a computational geodynamic setup, so we can try to quantify the forces that are involved. Yeah, thank you.
Preguntas? No? Yeah, I have a curiosity. There are no sediments involved. I mean, sediment from the upper plate involved in this collisional system. Yeah.
There are sediments, but on this map, they would be all the way down here.
Okay.
So the initial portion of the slab is pretty much all metabasalts. And then as you sort of go structurally downwards, you get more and more sediments. And the argument is maybe that this portion was just too hot and all the sediments melted out. Or that as the slab sort of gets closer and closer to the continental margin, you end up with more and more sediment in the system. So it's not absent, it's just not in the top part of the soil that we're looking at.
Okay, nice. We just as a comment, we had a similar behavior in terms of discrepancy between the lutetium, hafnium, and garnet and zircon ages in Guatemala, actually. In the Guatemala shooter zone, pretty similar ages, actually. All the evidence point to zircon ages of the collision, let's say, between 68 and 75 maybe million years. And lutetium hafnium in garnet suggests ages of around 90 million years. So that is even more different in terms of evolution. But again, it seems that in any case, the garnets by lutetium hafnium, at least they record the prograde something event, or the first high temperature event those are more ecologic grade, but they do have the same behavior.
Yeah, I would just comment on that and say, we now have the ability to date rocks by multiple isotopic systems. And every lab that does lutetium hafnium argues that their dates are right. Every lab that does uranium lead argues their dates are right. And I think what we're trying to do here is just make them internally consistent.
Yeah.
Can we plot all the data on each other's isochrons from different labs, from different places? I want to be careful how I say this. I think that the lab that did those initial dates, that there are problems. And I have been able to quantify what those problems are with our new data. But I think in your case, I mean, there are tectonic reasons or metamorphic reasons that could be different. So I think it's just a case-by-case thing, and we just have to recognize that maybe there are geologic differences versus analytical differences. But if we want to understand the geodynamics, we have to exclude the analytical differences. Yeah. Otherwise, we're dealing with metamorphic durations that aren't.
And I mean, and now we know that also if you just take into account one isotopic system, uranium lead, for instance, you still have sometimes those 2-3% different from my lab to your lab, and another one. So again, once you propagate those differences at these scales, and especially because many times those are measured only in standards, which should be identical, and at the end we know they aren't, so things get even more complicated. Okay.
I have another question.
Yeah.
About those zircon ages that you showed, that you mentioned that there are kings, uranium lead. There's something conspicuous about it. I mean, I assume that there's some patholuminescence images showing that there's no overprinting, that there's the first generation, that there's nothing, there's no mixing that or something, because you're not dating different generations that are probably biasing your data, I guess.
Yes, I'm glad you made that point. First of all, I'll say that paper just got published this year in Journal of Metamorphic Geology. And unfortunately, it's painful to read because we went through all those discussions. What we did is we mounted the zircons in epoxy mounts. We performed cathodoluminescence imaging to exclude cores or the influence of inheritance. We then did laser ablation on all the zircons, including different portions of it to get the trace elements. Then my colleague actually plucked out individual pieces of the zircon, and we actually used lasers to etch out different portions of the zircon that we knew had one consistent trace element and cathodoluminescence profile, and then he dated them by TIMS. So I agree, it's definitely worth considering, and that's something we've tried to model as well. But as far as we can tell with our analytical workflow, we've been able to exclude the evidence of inheritance of these things. Yeah, but very fair point, something to consider.
Bueno, si no hay más preguntas, muchas gracias, George.
Muchas gracias.